We're ready to begin lesson 14, and they call it isotopia, but really we're looking at stable and radioactive isotopes. And I know I wasn't there for the kind of the end of the last section and the beginning of the introduction for isotopes, but what I want you to do is just take in as much as you can, write down any questions that you have as we go along, and I'll make sure I answer those when we get back. It was kind of a bad time for me to be gone 3 days and have a snow day and a half day in between. So I'll be back on Friday. I could explain all of it to you. No need to panic, but you really want to pay attention and take in as much as possible. So the number one thing to remember here is that an isotope are atoms of the same element that have different number of neutrons. The number of protons will be the same. The number of electrons will be the same. The number of neutrons will change. And so remember that protons and neutrons together make up the mass of an atom. So if you have more or less isotopes in an element, then you can have atoms of the same element with different atomic masses. And we'll see that as we go along. Sorry about that. On the second frame, it says chem catalyst. And remember, a catalyst is something that you put into an equation that gets things going. So what they want you to do is think about what you already know. And you guys might want to have a periodic table out in front of you. I'll be bringing one up on and off as we do this. So you might want to have your periodic table in front of you if it's from your book or your paper one. Which of the following are isotopes of copper? Cu. Explain your reasoning. So if an isotope is an atom of the same element with different numbers of neutrons and nothing else changes, you always want to go to the identity of copper if we're looking for copper. So when you bring up the periodic table, I'm going to bring mine up. Here's copper right here. And do you remember which number is the identity element? It's the atomic number. Atomic number tells you how many protons. The average atomic mass, when we round it, will tell us the number of protons and neutrons together. So when we come back to copper, the identity of copper is 29. It cannot be copper unless it has 29 protons. So you might remember from the last particular thing we did with the last lesson, you'll notice that we learned to write an isotope's formula by writing the letter Cu for copper and then writing the mass, a possible mass on top, and the definite atomic number on the bottom. So atomic number gives us the identity. So quickly looking through here, there's one that we could easily see doesn't belong. If Cu is the proper formula or lettering symbol for copper, then this could be, this could not. So already we get rid of letter B. All the rest have Cu, so that's one thing we can look at to say that the rest might be copper. If you go back to our formula, or back to our periodic table, you can see that the atomic mass must be 29 for it to be copper. When I look here, this has 29, so A is a possibility. Copper with a 28, not a possibility, so we're going to get rid of now B and C. This copper has 29, that's a possibility. A and D are still in. Letter E has 29, that one's still in, and letter F has 29, that's still in. So we've gotten rid of these two, and these four are still in. When we go back and look at copper, go back and look at the periodic table, we see that copper's average atomic mass is 64. That means that the most abundant form of copper out there has an atomic mass near 64. So we'd have 29 protons and 64 minus 29 neutrons in the most common form of copper. So we know that the atomic mass of all the rest of the coppers out there have to be somewhere pretty close to 64. So let's go and look and see what else is left. Copper with atomic mass of 63. That's a possibility. Copper with an atomic mass of 87. That's very high. That is not a possibility. Copper's average atomic mass would be a lot higher than 64 if that was in there. Copper with an average atomic, or an atomic mass of 34. That's too low. If they had one with 34 in it, then the average mass would be less. And copper with a 65, that's a possibility. So here's what we're looking at. We know that this one can't be copper because it doesn't say Cu. We know that this one cannot be copper because it has 28 protons instead of 29. We know that this one is possible because it's very close to the average atomic mass of 64. This one's very possible because it's close to the average atomic mass of 64. This is too low for the average atomic mass. This is too high for the average atomic mass. So A and F are our best choices when we're looking for that. So while it took us a while to reason all of that out, you guys will get better at that. Go automatically look for the symbol. Second, look for the number of protons. And then start looking for an atomic mass that's close to the average on the periodic table. So it says, what types of isotopes do the various elements have? So we're going to look at that as we go through. And by the time you are finished with this lesson, you should be able to interpret a graph of naturally occurring isotopes. You should be able to describe the general nuclear composition of a stable nucleus. You should differentiate between a stable isotope and a radioactive isotope. And while that all sounds pretty tough, it's all about numbers. And we'll look at the numbers and I'll show you how to kind of signal when you have a radioactive isotope. So you're going to work together in pairs as we always do. You should each have a copy of your periodic table, and I forgot to list that on here, but you're also going to need a copy of a isotope chart. So I'm going to show you that isotope chart before we get going. We're going to look at a graph, and this graph, and I'll bring it up real quick, this is what you should have in front of you. Let me get past all of this. This is what it should look like. So it says chart of naturally occurring isotopes. So if you don't have that in front of you yet, go ahead and grab that because I'm going to teach you how to read it first before we actually do the lesson. I'm going to shrink that back. The graph of naturally occurring isotopes gives us an idea of how many different isotopes of all the elements are found in nature. The words atom, isotope, and element are interrelated. They do not mean the same thing, but they are very, very closely tied together. So those are words that you guys want to make sure they were part of your vocab list. You want to make sure you really study those so you can tell the difference between the three. The straight line on the graph represents a 1-to-1 ratio between the number of protons and neutrons in an atom. So let me bring that back up and show you what that means. Any elements that are on this line going up through here have 1 proton for every 1 neutron, or I should say it the other way around, 1 neutron for every 1 proton in the nucleus. So as you can see, when you're going up this line, it all stops right about here, the 1-to-1 ones. They have to be sitting right on that line. And then after that, we notice that it goes way far away from the line, which means that all of these elements that are up in here have a lot more neutrons than they do protons. And there's a reason for that. If you remember when we were doing the build an atom activity, if you had a lot of protons in the nucleus and you didn't have at least 1-to-1 neutron, and when we got bigger atoms, more than 1 neutron in there, the isotope or the nucleus began to jiggle around. It was unstable. We'll look at another model. I'll have another model for you guys to practice when I get back in class. Okay, I'm going to shrink this down one more time to make sure there's not more information you guys need. No. Okay, so let's look at the graph for a second. Wrong thing. Alright, so let's look at the graph for a second. On the side, on the left-hand side, you see neutrons. On the bottom, you see protons. And then on your graphs, it may be a little hard to see, and you might want to actually look at the graph in your book to see it better. But anything with a dark black box, the little dark black squares, are the most abundant isotope of that element. The ones that have a little gray square are other isotopes that are found in nature, and anyone with an open square, like a white square, is a radioactive isotope. Let's see if I can make this a little bit bigger for you guys so we can look at it closely. Okay, So when we get to looking, if this is number of protons, then you can look at atomic numbers on your periodic table and identify the elements. And over here's our number of neutrons. So what I'm going to look at first is this number 5 right here. Whatever element 5 is, and let's go look at our periodic table and find it. Element number 5 is boron. Okay, now if you look at boron, its average atomic mass is 10.81, so we could round that to 11. We subtract 5. We know that there's a form of boron out there with 6 protons. So we're going to go look and see if it's on the chart. So let's look at the chart again. There's 5 protons right here, and if we come across, we know there is a form of boron with 5 and 5. See how it's got the little gray box right there? Gray box means that there's other forms of boron out there that we didn't know or that we know about. And then if you go up to the black one, that would be 6 neutrons. There's really not a mark over here, but 5 protons, 6 neutrons. So remember, that would be, the black one would have the atomic mass of 11, 10.8, whatever that is on there, 10.81 is very close to 11. The most common form of boron is boron 11 with 6 neutrons and 5 protons. So we see that in the black box there. That's the most abundant form whenever it says the little black box. Let's move this over. It's your most abundant form. So 5 and 5 right there. 5 and 6, sorry. At 5 and 5 there is another form of boron, and we would call that boron 10. 5 protons, 5 neutrons. So let's go up to number 10. So on our periodic table we could see that number 10 is neon. Neon has an average atomic mass of 20.81, so we round that to 20. 20 minus 10 is 10. So there should be a form of neon that has a mass of 20, but it has 10 protons and 10 neutrons. So let's look at that. Sorry, I'm clicking. So here's 10, and we go up the line, and there it is. Right there on the line is the black 10 and 10. That's the most abundant form of neon. But if you go on up, there's a neon with 10 protons and 11 neutrons. That would be neon 21. And there's also one with 12. Okay, so we've got 12 neutrons and 10. So neon 22. So we have a neon 20, 21, and 22. So that's how you read these charts. You go on and you read them through, and I know it's a little bit tough to read, especially when you're reading the one on the paper that I gave you. You might want to go to your book and get a ruler to read those, or you could actually bring this up. I put this online for you guys. If you brought it up, you could bring it up on Microsoft Word or Adobe. I don't know which one I have it on. And you could bring this up closer so you can read it. Okay, we're going to stop with that part right there, if you'll stop this one, and then get your worksheet for Lesson 14, and we'll go through the Lesson 14 sheet together.